Dear students, continuing with the reviewing of question paper, December 19, January 20, today we will take up module number 3. Module number 3 basically deals with a transformer and domestic wiring. Question number 5a, derive an EMF equation of a transformer with usual notation. You have to derive the EMF equation for a transformer. For that, first you have to write how exactly the transformer, the induced voltage is inducing in a transformer windings. That is, we know that when a AC supply is given to the transformer, an alternating current is flowing in the primary winding, which creates the alternating flux. That flux is linking both the primary and secondary winding. It is alternating in the nature because of there is a change in the flux which is linking with the conductors of primary and secondary winding. There is a induced voltage by Faraday's laws of electromagnetic induction. The same thing is written here. When alternating supply is given to the primary winding, it produces an alternating flux in the core material. It links with the secondary coil also. That is the flux produced by the primary winding which is linking both primary as well as the secondary. In accordance with the Faraday's laws of electromagnetic induction, there is an induced EMF in both primary and secondary winding. Then, what are the nomenclature we are using for EMF equation of a transformer? The first one is the phi, that is the flux produced in the core due to the primary winding. It is alternating in the nature given by phi max sine omega t. Then phi max is the maximum flux in the core. Okay, if you want to express the phi max in terms of flux density and the cross-sectional area of the core, that is Bm into A, or in other words, the flux density is equal to the flux divided by cross-sectional area, otherwise the flux is equal to the flux density multiplied by the cross-sectional area, where Pmax is the maximum flux density in the core. It is measured in terms of Weber per meter square. A is the cross-sectional area of the core in a meter square. Then N1 and N2 are the number of turns in the primary and secondary windings respectively, whereas F is the supply frequency. These are the nomenclature you are using in the EMF equation of a transformer, where E1 is the RMS value of the primary induced voltage and E2 is the RMS value of the secondary induced EMF. Now we know that according to Faraday's laws of electromagnetic induction, the magnitude of the induced voltage is given by, it is a rate of change of flux. For the transformer, we will see that induced EMF of the transformer is proportional to product of number of turns and the rate of change of flux. That is, N is the number of turns which is linking with the number of conductors, and there is a rate of change of flux that gives the magnitude of the induced voltage. Therefore, magnetic flux phi increases from 0 to its maximum value, that is phi max, in a 1/4 of a cycle. You can see the waveform here. It is the waveform of a flux. Then it attaining its maximum value at 1/4 of the time, the total time period. You can see here, for completing one complete cycle, the time taken is a t, that is a t. Then we are interested in the time taken for 1/4 of a cycle, that is equal to 1/4 into t. Therefore, the change in the flux from 0 to its maximum value, it will take place in 1/4 of the time period. The same thing is written here. The magnetic flux phi increases from 0 to its maximum value, phi max, in the 1/4 of the cycle. Therefore, d phi is the change in the flux is the initial value is 0, the final value is phi max. Therefore, phi max minus 0 is equal to phi max, and time taken is 1/4 of the total time period, 1/4 into t. T can be replaced by 1/f. Therefore, dt, what I am getting here is 1/4f second. Then in a EMF equation, if you are substituting d phi and dt, then what I am getting is the average induced voltage is N into phi max in the numerator, because the d phi is phi max and dt is 1/4f. Then bringing this into the numerator, what I am getting is 4 5 max Mf into N volts is the, it is a volts VOTS, that is, it is, there is spelling mistakes here, it is a volts here. Then the average induced EMF is equal to average rate of change of flux into number of turns. Average induced EMF is equal to average rate of change of flux into number of turns, that is nothing but it is N into 5 max F in F. That is average induced EMF is given by 4 5 max F into N volts. It is the average induced EMF. What we are interested is RMS value of the induced voltage. For that, what you have to do is you have to multiply 1.11. Therefore, the phi is very sinusoidally, the RMS induced EMF is you are getting by multiplying 1.11. Therefore, the ERMS is the general equation, what I am getting is 4.445 max F into N into volts. This is the induced voltage in the winding. It is a general form of equation. If you are taking this EMF equation for the primary winding, the N is replaced by N1. If you are taking this equation for the secondary winding, then you have to replace N by N2. Therefore, what I am getting here is the E1 is equal to 4.445 max F into N1 volts, and the E2 is equal to 4.445 max F into N2 volts. This is how we have to derive the EMF equation. That is very simple. That is, the EMF equation is given by Faraday's laws of electromagnetic induction. That is, the magnitude of the induced voltage is given by N d phi by dt. The change in the flux from 0 to maximum value is phi max. Therefore, d phi is phi max. And time taken for changing from 0 to phi max is 1 by 4t. The t can be replaced by 1 by f. So that dt, what I am getting is 1 by 4f. Then if you are substituting in this equation, what you are getting is the average induced voltage. Then to get the RMS value, what you have to do is you have to multiply 1.11, so that what I am getting is 4.445 max F into N volts. Then if you want to write the equation for the primary and secondary voltages, then you have to multiply respectively N1 and N2, so that what you are getting is the primary induced voltage 4.445 max F into N1 volts, and E2 is equal to 4.445 max F into N2 volts. Then the question number 5b, what he asked is explain the two-way control and three-way control of a lamp with a suitable circuit diagram and working table. That is, you have to draw the diagram for the two-way control and its switching table, and you have to explain step by step. I am drawn here, there are two switches with three terminals. That is 1, 2, this is a common, it is 1, 2 and a common here. Then I have got a switching table. Just you have to write the different combination of switch position, whether the bulb is on or off, if you are giving a supply to the circuit. That is, if it is both are 1, you can observe there is a connection here 1, 1, and because when it is 1, 1, there is a flow of current here, then there is a light will be on. Then when it is 1 and 2, that is 1, when it is 2, then there is no connection, there is bulb will not glow. And in the third position, both are at a 2, 2. You can see 2, 2, the bulb will glow, that is on. Then the fourth combination is, the first one is 2, second one is 1, therefore bulb is off. This is how we have to explain the two-way control of a lamp. Similarly, we have to go for three-way control lamp. Once again, you have to draw the circuit diagram. We have got three switches here. One is an intermediate switch, the another one is two-way switch on the either side. Then these are the connecting wires. Okay. Now we can test for the different combinations. Here there are the intermediate switch has got two different portions. One is the AB and CD connection, the another one is AD and CB connection. Then the positions are here 1 or 2. Here either it is ABCD or it is ADCB. Then these combinations are given, just you have to trace it. Just I am taking for one of the example, when the first one is connected to, the first switch is connected to 1, then the second is also 1, that is the first position what I am showing, it is 1 and 1, and the intermediate switch are connected to A, B and C, D. It is A, B and C, D. Then you can see here, if the supply is given here, then the current start flowing here, then here, next there is a complete path, because of that the bulb will on. Therefore it is 1, 1, A, B, C, D, it is on. You have to trace the path for the current. If it is a closed path, then the bulb will on. If it is disconnection in between, because of the switches, the bulb is off. If you are looking to the second combination, both are at 1, 1. However, the connections of the intermediate switch is changing from AB to AD, CD to BC. That is, it is AD and CD. If it is AD, the current will entering into here, and it is passing through here. Then here there is a discontinuity of the supply. Because of that, the bulb will not glow. Therefore, it is off. Similarly, all the combination you have to explain the three-way control. Then 5C is asked the numerical on a transformer efficiency. What he asked is, a 40 kVA single phase transformer has a core loss of 450 watts and full load copper loss of 850 watts. If the power factor of the load is 0.8, calculate full load efficiency, maximum efficiency at unity power factor, and load for a maximum efficiency. These are the things he asked for the transformer. First you have to list out the data given. It is a 40 kVA transformer. Iron loss is 450, irrespective of the load condition, it is constant. Then the copper loss at full load is given as 850 watts, and at 0.8 power factor you have to find out full load efficiency. For unity power factor you have to find out maximum efficiency. First, the equation what we are using is a standard equation for efficiency is, it is x into kVA into 10 raised to 3 into power factor divided by, it is nothing but output. Here output plus iron loss plus copper loss. Here the first what he asked is full load efficiency, straightforward, means here x is equal to 1 because it is a full load, and at 0.8 power factor he asked you to calculate the efficiency. Therefore power factor is 0.8. kVA is given, iron loss is given, copper loss at full load is also given. Just you have to substitute and you have to find out the efficiency. That is what you are getting is 0.9609, or you are getting in the percentage it is 96.09. Now the second what he asked is the maximum efficiency at unity power factor. To calculate the maximum efficiency, first you have to calculate at what load the maximum efficiency will occur. Then only you have to proceed. Then what is the condition for our maximum efficiency? It is iron loss is equal to copper loss. That is the condition for maximum efficiency. We will go for a 3, then we will come back to the 2. That is nothing but condition for maximum efficiency is equal to x square times copper loss at full load is equal to iron loss. That is x square I am adding here because I am taking copper loss at full load. That is x square times copper loss at full load must be equal to iron loss at that particular instant of time. There is a maximum efficiency occurs. Then what is the value of the x? You have to find out, because WCUFL is given, WI is given, the load at which the maximum efficiency occurs is x, that can be calculated, that is under square root WI divided by WCFL, that is under square root W divided by WCFL. Then what you are getting is 0.727, means at load 0.727 the efficiency of the transformer will be maximum. At this particular condition the efficiency of the transformer will be the maximum. Therefore the second point what you have to do is maximum efficiency at unity power factor. For calculating the maximum efficiency, what is the x now? X is 0.727, because at this particular instant of time there is a maximum efficiency will occur. Therefore, what I am writing here is X is 0.727 and at unity power factor he asks you to calculate the efficiency. Therefore, 0.727 is the loading factor, power factor is 1. Once again I am substituting all the values in this equation, so that what I am getting here is the maximum efficiency will be 0.9699, or it is 96.99% is the maximum efficiency. It is very simple. To the point you have to do it. That is what is asked. Then you have to write the efficiency equation. The based on the condition of the maximum efficiency, that is X square times copper loss at full load must be equal to Wi. Then you have to find out at what particular load the efficiency will be maximum. Based on that you have to calculate X. Thereby you have to calculate the maximum efficiency of the transformer. In the next session we will see the question number 6 ABC.